So now we'll get to solving this optimization problem so that we can find out what is the capacity uh, under the conditions where both the transmitter and the receiver side have the channel side information, and we're also doing what is called the power control. So remember, this is what we have. This is optimization problem we have. We wanted to maximize this capacity, and because this was rather than maximizing the capacity, we have tried to write this optimization problem in its standard form. So in the standard form, we would write it as a minimization problem. So we would be minimizing the minus of the function, which represents our capacity, and we would be minimizing over Pj. Here Pj is the transmitted power when the channel is in the jth state. And the constraint under the standard form would change to this constraint, that is summation j equals to 1 to capital N, pj tilde minus p bar, so p bar comes on this side, is less than or equals to 0. So under the standard form, you must have 0 on the right hand side. So you have one major constraint. This is the major constraint, and this is your objective function. So we would solve this optimization problem using what is called the method of Lagrangian. It is also called the primal dual optimization. So this constraint optimization problem, where you have an objective function to be minimized, followed by some constraints. In the method of Lagrangian, this constraint optimization problem is changed into a unconstrained optimization problem, where you formulate what is called the Lagrangian function. So we would write down what is the Lagrangian function for this optimization problem. So the Lagrangian function for this optimization problem, J, so J is the letter used in your textbook. It would be a function of your optimization variable, which is Pj here, and that would be equals to your objective function, that is minus summation j equals to 1 to capital N b log base 2 of 1 plus Pj gamma over P bar times Pj tilde plus some Lagrange multiplier, we call it lambda, times your constraint function, which is summation j equals 1 to capital N Pj, Pj tilde minus P bar. And that is your Lagrangian function. So in order to solve this primal dual optimization problem, the necessary and sufficient conditions are what are called the KKT conditions. So KKT conditions are to be observed. So one of the KKT conditions, if your primal problem or your objective function is convex, is that the derivative of this Lagrangian vanishes at the optimal point. That means all you need to do is to take the derivative of this Lagrangian function, take the derivative with respect to your optimization variable, equate that to 0, and that Pj would give you the optimal value. So let's try to take the derivative of this function with respect to Pj. So that would be equal to, remember you're talking about one particular j, so where this j is taking values from 1 to capital N. For all other values of j other than this particular value, that the derivative would be 0. So you would have only one out of these n values for which you would have so here this j was varying from 1 to n. Here you have fixed j. Hence, out of these n different variables, you would have only one term that would be non-zero. For all other values of j, that would be equal to 0. So hence your derivative of the function with respect to pj would be equals to minus b over natural log of 2. That would take care of the change of the, because the base is 2, times 1 over 1 plus pj gamma over p bar times pj over p bar times pj tilde that is pj tilde was already here. So here we have pj tilde, and this pj over p bar is because you have taken the derivative of this function with respect to the log, and then you need to multiply the derivative of what of your objective of the function in the denominator here. So the derivative of this term is 0. Derivative of this term would be pj over p bar. Hence it gets multiplied here, plus lambda times again. You would have only one out of these n terms to have a non-zero derivative. So that would be pj tilde, and then you would equate that to be equals to 0. You would equate that to be 0 and compute what is your pj over p bar, for instance, and that would give you the power control for this optimization problem. So the rest of the things are just mathematical manipulations. You would want to solve this Lagrangian in order to find out what is pj over p bar. So let's try to solve that. So first you can take this on the other side. So you would have, and then you can multiply this term in the denominator on the other side. So let's see what happens. So you have, so there's a minus sign here. You would take this to on the negative side. You would have a minus sign there. Both of those would cancel out. So on this side, you would have b over natural log of 2. You would take this term to the other side. So I'm not going to write this, times, sorry, this should not be pj over p bar. This should be gamma over p bar because you're taking the derivative with respect to pj, times gamma over p bar, pj tilde would be equals to lambda pj tilde times 1 plus pj gamma over p bar. That's what you have. Pj tilde gets cancelled out by this pj tilde. And then you have this term left. So pj gamma over p bar. You can take lambda on this side already before doing that. Would be equals to b gamma over natural log of 2 times lambda p bar. So lambda comes here, minus 1. And then all you need to do is to divide both sides by gamma, and that would mean your pj over p bar, so you have solved for that, is equals to, you have already a gamma here, so that cancels out, b over natural log of 2 lambda p bar minus 1 over gamma. So let me introduce another term here. So let me call this term to be equals to 1 over gamma naught. So if this term is 1 over gamma naught, remember b is a constant, natural log of 2 is a constant, p bar is a constant, lambda is your Lagrange multiplier, you can find out, and then if once computed, it's a constant. So we call it 1 over gamma naught. It needs to be computed, but nevertheless, let's call it 1 over gamma naught. So now you have this power control. It's a very interesting equation that the power control Pj, the amount of power which would give you the maximum amount of capacity, the maximum capacity is equals to simply 1 over gamma naught minus 1 over gamma. And since this power must always be positive, there is a way of representing that. You write it in this fashion, and you write a plus here. That means uh, you would give this much power into the channel for the jth state if the 1 over gamma naught minus 1 over gamma turns out to be positive. If 1 over gamma naught minus 1 over gamma turns out to be negative, then you do not put any power in the channel. So in order to visualize this solution is also called the water filling solution. You can think of, suppose you draw what is 1 over gamma. So if on this axis you have gamma, for example, increasing gamma. So 1 over gamma would have this kind of a decreasing function if you are talking about a discrete time function. So for example, if your gamma is really large, then your 1 over gamma would really be small. And if your gamma is really small, then 1 over gamma would really be large. And then this term 1 over gamma naught is called the water level. Right? So let me draw the water level here. Suppose this is your water level. This is 1 over gamma naught. Right? And you can think of, so this is the water level, and this term, this remaining term here, this shaded portion which I'm drawing, can be thought of 1 over gamma naught minus 1 over gamma, which is nothing but the power you're going to pour in into the channel if the channel is in this state. If your channel is in this state, then you would pour how much power? You would pour more water in it. So this much power you would pour into the channel. So this kind of a solution is called a water filling solution. That means that if 1 over gamma naught is your water level, you would fill in the water or you would pour in power unless till the time your you reaches that water level. So that means your power you would insert into the channel would be 1 over gamma naught minus 1 over gamma, where this thing which I draw 1 over gamma can be thought of as the base of the container. So you have the base of the container, you have a water level beyond which you cannot go. If for instance in this state you have your 1 over gamma is less than 1 over gamma naught, you would not pour in any power at all. So this is a state which your channel is so bad that you would don't want to insert any power into the channel, and that is your optimal solution. So how would you compute this gamma naught, 1 over gamma naught, or the water level? That we would talk in the next video.